All right, let's dive right into this explainer and decode the invisible rules that actually govern how atoms interact to build the physical world around us. I mean, have you ever stopped to wonder why a hard grain of salt acts so completely differently from a fluid drop of water, even though they're both just collections of atoms? Today, we're going to unpack the secret social lives of these particles. We'll see how they bond, how they share, and how they sometimes outright steal from each other to create literally everything in the universe.
And a lot of this goes back to the pioneering chemist John Dalton in 1808. He essentially realized that atoms are like cosmic Lego bricks. You can't just mash them together however you feel like it. They combine in very specific, predictable, whole number ratios to build stable structures. You're never going to find half an atom in a molecule. Grasping that simple rule is pretty much the key to unlocking the rest of chemistry.
So here's our game plan for today. Dalton's atomic rules, covalent bonds, ionic bonds, writing chemical formulae, and real-world properties. Let's kick things off with Section 1, Dalton's atomic rules. Dalton laid down the fundamental law that atoms are the indivisible building blocks of reality. They don't just magically appear out of thin air, and they don't vanish into nothingness either. During a chemical reaction, they're really just rearranging themselves to find a more stable setup. The universe is basically playing this massive, endless game of molecular musical chairs, constantly shuffling the exact same basic pieces around to build entirely new things. Which brings us to Section 2, covalent bonds and sharing electrons. Think of a covalent bond as atoms agreeing to pool their resources. Every atom's ultimate goal is to have a completely full, stable outer shell of electrons. Those are called the valence electrons. If an atom comes up short, it can team up with a neighbor. They share electrons, so both end up totally satisfied and stable. It's a true cooperative partnership. Imagine a couple of hydrogen atoms. Each one only has a single electron, right? But that inner shell really needs two to be stable. By coming together and sharing their single electrons right in the middle, they form a stable pair. Now, both nuclei get to claim that shared pair, tying them together into a superstable H2 molecule. They are officially linked by a single covalent bond. And atoms can absolutely multitask to get what they want. Oxygen, for instance, has 6 electrons in its outer shell, but it's desperately looking for 8. It's exactly 2 electrons short. So it perfectly solves this dilemma by striking up sharing agreements with 2 separate hydrogen atoms. It shares 1 electron with the first hydrogen and 1 with the second. Everyone's outer shell gets filled, everyone is stable, and boom, you get a molecule of H2O, water.
Moving right along to Section 3, ionic bonds and transferring electrons.
Now, sharing isn't the only way to bond. Take sodium. It has this one lonely electron in its outermost shell, and it would be infinitely more stable if it could just ditch it to expose the full shell underneath. Then you have chlorine, which has 7 outer electrons and is aggressively hunting for just 1 more to finish its set. It's a match made in heaven. But instead of sharing, sodium just completely hands its electron over to chlorine. No takebacks. And because electrons carry a negative charge, giving one away or taking one on completely flips the electrical balance of the atom. When sodium loses that negative electron, it becomes a positively charged ion, or a cation. When chlorine snatches it up, it becomes a negatively charged anion. And you know the rule, opposites attract. These newly charged particles are violently pulled together by electrostatic forces, locking into an ionic bond. This is where it gets really cool. Because those intense electrical charges are radiating out in every single direction, ionic compounds don't just form isolated little pairs like covalent molecules do. They lock into these massive, repeating 3D crystal structures. Every positive sodium ion gets completely surrounded by negative chloride ions, and vice versa. It builds up those beautiful geometric crystals of sodium chloride, which is literally just the table salt sitting right in your kitchen. So the major takeaway here is the contrast. Covalent bonds are all about sharing to create distinct, independent molecular units, like a solitary water molecule just floating around. Ionic bonds are about a permanent transfer of electrons that builds massive, rigid, highly structured crystals.
Next up, Section 4, writing chemical formulae.
Now, writing these chemical formulas out might look a little intimidating at first glance, but it's really just a simple decoding puzzle with 3 easy steps. First, write down the letter symbols for the elements. Second, jot down their valency, which is basically their bonding capacity or charge. And third, just crisscross those numbers to the bottom of the opposite element. Let's try it. Say we're combining hydrogen and sulfur. Write your H, write your S. Hydrogen has a valency of 1,
Sulfur has a valency of 2. Crisscross them. Bring the 2 down to the hydrogen and the 1 down to the sulfur. We always drop the 1 because it's implied, and you easily get H2S, hydrogen sulfide. It tells you exactly what you need, 2 hydrogens to satisfy 1 sulfur. The exact same rule applies to ionic compounds. Calcium forms an ion with a 2+ charge, chlorine is a 1- charge. Cross the 2 from calcium down to chlorine, and the 1 from chlorine down to calcium, and there's your formula, CaCl2. 1 single calcium atom perfectly balances out 2 chlorine atoms.
There's just one tiny grammar rule to keep in your back pocket. Always simplify your ratios. If you crisscross magnesium with a charge of 2 and oxygen with a charge of 2, you'd technically write Mg2O2. But chemistry is all about efficiency. A 2-to-2 ratio is just a 1-to-1 ratio. So you divide by that common factor, drop the 1s, and magnesium oxide elegantly becomes just MgO. And finally, Section 5, Real-World Compound Properties. How an atom is bonded completely dictates how the bulk material actually reacts in your hands. You can easily test this with a basic electrical conductivity setup. Drop a substance into water, hook up a battery, put some electrodes into the solution, and see if the mix completes the circuit and lights up a bulb. Those independent covalent molecules, things like camphor or naphthalene, usually won't dissolve well in water at all, and they absolutely do not conduct electricity. But ionic compounds, since they're made entirely of charged particles, they dissolve super easily in water. When they do, those charged ions break apart, float around freely, and perfectly complete that electrical circuit to light up the bulb. And think about melting points for a second, because those 3D ionic crystals are locked together by such intense electrostatic forces, you need a massive amount of thermal energy to break them apart. That is exactly why salt has an incredibly high melting point. Covalent molecules, on the other hand, are just individual units sort of hanging out near each other. The bonds holding the individual molecules to one another are relatively weak, so they melt and boil at much, much lower temperatures. But there's a catch regarding the state of matter. While ionic compounds like sodium chloride or copper sulfate are fantastic conductors when dissolved in water, they will not conduct a single volt of electricity when they're dry solid crystals. Why? Because to conduct electricity, charged particles actually have to be able to move. In a solid crystal, those ions are completely frozen in place by those massive forces. So we've seen how these tiny, invisible atoms combine, either by sharing or outright transferring their electrons to build literally everything we interact with. If Dalton was right, and the mass of the universe is just constantly being rearranged, it means we are endlessly shuffling the exact same cosmic alphabet. Which leaves you with something wild to think about. With over 100 elements on the periodic table, what incredible, world-altering chemical combinations are just out there, waiting for us to discover them? Thanks for joining me on this explainer, and keep exploring.